there's maybe a very few people taking this kind of like people taking more, especially for identity.
You can share with us so we come to start.
You can the next like 500K, like
Yeah,
GPT.
Oh,
No, but there's a lot of media, like, who are like, AI, then just kill people and start like.
After class we have a power.
Sure.
Okay, so it's getting a little busy during this semester. So I hope we are still powering full steam ahead. So today is week 9. We cover transfer learning. So you guys can all join the Kahoot first. Then we'll go through the Kahoot which Long has prepared. So he'll be narrating the Kahoot for us. So we'll wait for at least, let's see, we have about at least 15 people, I think, in total. So I hope you all join. And then when we get to 15, we can start.
It's our fault and the reason for so like for then so that's what composing stuff. So there was like the whole ball. Then what I do is even like example, we try to short then this the question is like so the output is like what do you have an instance that the next one bringing like a function so they can like form of the so if for my one right now I think it's because I have a struggle I certainly need to use them then if it does get how do I say then it's like more I think more like make the code like more specialized universities because maybe some of the very good so you might want to do that so are you oh yeah I mean yeah like
Oh, we keep on losing people.
huh?
What? We're down to 8. So you who were in got kicked out.
Disappearing.
Oh,
me. No, because what happened? My phone fell asleep. What is going on?
It's not very stable today, is it?
Don't know. It just disappears.
Smaller and more insurance because it's a so small and the most is it's around one of the moment so yeah.
Okay, well, we'll give it another 1 minute or so. Hopefully, more of you will be able to log in.
So like
We're trying to get to a quorum of 10. Okay. Anyone who hasn't logged in? Nine.
Wouldn't let me go in.
One more. 10. Okay, we have 2 more people who just came in, so we'll wait for you. 11. Yay.
Generate this.
Okay, I think we are ready. The Isong Pro here and our graphics cards are ready to go.
Yeah, I got it.
Okay, Long, all over to you.
Okay, thank you, Professor. I finished. Yeah, so the first question is, do you think LLMs can reason?
A big question.
Yeah, you can use the microphone.
Uh,
Oh, yeah. So I think many people think that LLMs can reason. And many people also think that LLM can't reason. So for example, in ACL 2023, Jeff Hinton spent like more than 1 hour just try to persuade people that LLMs can reason by his talk to pass to the intelligence. So, but later on, I think last month there was a paper saying that GPT-4 can't reason. So it is still a controversial question. Yeah, so that's why I put here yes or no, or yes and no, and or it is controversial question. So. So the next question is, what are the core aspects of common sense knowledge?
oh,
Yeah, so the core concept, the core aspects of common sense knowledge is are fairly widespread and reasonably stable. It should not be shared human experience. It also should not be just information acquired through formal education. And it should not also be just a formalized and universally accepted set of facts. So the next question is, increasing the model size is likely to bridge the gap between human common sense and also machine in the near future. True or false? Oh, interesting. So yeah. So I think in the lecture note about the common sense, so there was a figure saying that increasing the model size is not like likely bridge the gap between human common sense and also machine common sense. You can take a look at the lecture in the previous week again. So the next question is, why do we need LLMs to faithfully reason? Wow, okay. So so it's a little bit interesting. So let me try to explain to you. Let me try to persuade you. So it should not be just to improve the ability to tell compelling stories, right? Because LLMs always tell compelling stories. It should also not be just to make informed and rational generations, because every time you see that the generations of LLMs are very rational, and yeah, like it seems that the generations are relatively logical, right? But if you refer to the paper of DeepMind, I think about faithfully reason. So the purpose why we need LLMs to faithfully reason is to reduce the level of opacity, and it allows verifying the answer. And the last option is obviously not so true.
So what's the meaning of opacity?
Oh, opacity is like the value of the answer. So it is like, for example, machine say something, but if they like specify step by step, then we can somehow verify it. But let's say if it's just say a lot of things, it seems reasonable, then it has nothing there. That's why we need flexibility.
So it's like the interpretability of the model.
It should not be just interpretability of the model, but it should be also the interpretability of the answer. Yeah.
Opposite transparent.
Okay.
Yes.
Yeah, so you can refer right to the DeepMind paper. I read all the papers before I really read the question. So the next question is, what are the key skills of Voyager? Oh, okay. So the key skills are exploring the world, acquiring diverse skills, and also making novel discoveries. So I think this one is. So the next question is, which one is one of the limitations of Voyager? Yeah, so this question is quite straightforward. So API calls and also incorrect skills generated, and also sometimes the framework also generate like unexist items in the game. Yeah, so we call that one as a hallucination. So the next question is, which aspect doesn't social simulacra cover? Oh, yeah, I think this question is a little bit hard if you haven't read the paper, but yeah, so the framework already covers the emergent social behaviors of the agents. Right? The framework also talks about the memory, how they manage the memory, and also the memory system of the generative agents. The framework also talks about plans and also reflections of the generative agents. Only the robustness of generative agents is one of the limitations or one of the aspects that this framework they didn't discuss. Okay, so you can find the limitation of the paper. Oh, interesting. Okay, so the next question is, PAR can work with weaker models, true or false? Yeah.
And our last question.
Yeah, the last question is, what is the difference between code prompting and PAR? Yeah, okay, so in PAR, because we need the model, because we need the models to like in some steps of solving the problems, we need the model to translate the problems into codes. So that's why we need a few short examples, like the examples for the model to like how to translate that one into codes and so on in the kind of like template format. So that's why PAR only works for few short. However, code prompting works for both shot, so that's also the answer.
So both shot means zero shot and few
Yeah,
shot?
yeah.
Okay.
Zero shot and few shot. So yeah. Yeah, okay. I'm done my cover.
Yeah.
Very good questions. Very nice to meet you.
Okay, so before we get started, I have a couple announcements. It's going to take a few minutes and then we'll get started with our transfer learning work this week. Okay, the first one is again that we have steps. Steps comes in week 13. It is on Wednesday night. Okay, so Wednesday night, 7 p.m. to 9:30 p.m. We will all be coming back to school to show off the projects that we've done. Okay, so this is again a mandatory part of this course. It requires everyone, including the 6101 PhD students who are in the first half, to come back and do this. Okay, so there are a couple different things that I need from you. And I've given some information on this in our channels. I'm just going to put it up. See what I can do that. In projects. Okay, is that we'll need your team member's name, okay, email and NUS.net. These will come from the worksheet that I just showed you, right? So here you have your name, your team ID, your NUS ID, and your email. Okay, so these things need to be accurate. If you're a guest, then obviously you don't have an NUS ID. You can just put NA for not applicable. Okay. Then we need your team name to be accurate because if you noticed here, there's a new worksheet, Steps Projects. Okay. Under Steps Projects, I've taken all of the unique identifiers for projects and listed out the team members. And we need you to give a project title and an abstract. Okay, so you can just make it a short 2 or 3 sentence abstract, okay, just to connote what's going on. And later on, you're going to also want, if you'd like, to create some media for your project. Okay, so during steps, what happens is that you will have a poster board, an A0 size poster board in portrait format. Okay, but you can also run it, I think, landscape. Okay, and then you can print the graphics on it. I'll give you a template later, but I'll show you samples of what that looks like. Okay, so yeah, I think there was one here that I put up. Yeah. Okay, so this was 6101 as run by my division, my research group a couple years ago in 2018. So we were doing conversational recommendation systems. Okay, and in fact, you can see some of the projects that were back then. So the students created some media for their cover image, and then they have a poster. Okay, so the posters, they're a critical thing that you need to produce because that's the one that's going to be printed free of charge, you know, on us. Somebody in our group will help you print it. Otherwise, if you're an SOC student, you can just go down to the basement and they have the large format A0 size printer. You can print it out. You can lug this very bulky thing around with you, or you can deposit it in our undergraduate office. And then on the night of steps, you can come pick it up and then tack it to your board. Now, steps this year has, like always, many different courses. There's almost always a game development course, but there's also our software engineering course. And this year they did AI projects too. So there are at least 5 AI projects where they're using LLMs, but they're not doing the technical part, they're doing the applications part. So it's also really cool to touch base with some of them. Okay, so I put up this link so that you can check out all of the projects that are here. And basically, again, that means you'll need all of these things, right? You'll need a cover image if you want to have one. You don't have to. You'll need, obviously, your title. And this is the abstract that's written here. Some people only gave a single sentence, and that's okay too. And then you'll produce a poster. You can have a homepage. If you have one, you can link it to GitHub or something like that. Okay, so this is the output of the project work that culminates all the activities that you're doing in teams or a solo to do all this work. Okay, so in part, we need you to fill out these two columns, D and E. Okay, touch base with your project groups either in Slack or WhatsApp or Telegram or however way you communicate, and then fill that out. Okay, and then later I will be publishing this to our current new events page. In fact, it's here already, but I think you might not be able to see very much. Okay, so this is the one that's happening. It's November 15th, just a little bit under a month away. And then you can already see that our large language model project is up. We have 0 guests registered because I need all of your information in order to populate the project tiles. And then you'll be given an email, which you can click a link, and then you can populate all of the information there. Okay. So any questions about that? So this week also happens to be the deadline, believe it or not, for development sprint 2, which is our 3rd sprint. Okay, it just seems like yesterday that you guys had to turn in the 2nd development sprint. It's actually every 2 weeks, right? So it does mean that we have to try to accelerate and make sure that we can hit our marks. If you are not meeting your own expectations for your development, that means you have to scale back. Okay, but it does mean you need to put in the requisite number of hours for the course in order to satisfy, as a PhD student, okay, at least the lab rotation, which is 2 MC or 2 units of about 60 hours in total. Okay, that includes time in the class. Okay, or if you're an undergraduate student doing it for 4 units, then 130 hours in total. Okay, and again, just to reiterate that, that is something that you can benchmark here. So if you go into our shared spreadsheet and you go to the end, again, I've said this a couple times, you need to fill in these rows so that we can tabulate how much time you spent. Okay, this is on an honor basis. Okay, you say I spent 100 hours this week, I won't believe you, but I'll give it to you anyways. All right, because I don't have the time to check everyone, but it's on a, I think we can try to be honest with ourselves here. Okay, so there's columns here for lecture hour. If you were doing 1 lecture, support role for your first lecture. If you happen to be doing it for 130 hours, or if you're, again, fortunate or unfortunate enough to be in my group, then you have to do both lectures, both lecture and support. And then you have 4 columns for project hours and then 1 for miscellaneous hours. Okay, so you need to fill that out. Hopefully you'll reach a total similar to what Yisong wrote here of about 60 hours if you're doing it just within 6101 or as a guest. Okay, all right, so that's all I have for you. So I'll close these and then we'll start our lecture. Okay, so if you can ask questions, do try to speak up. We have a microphone here, so you can the lecturer can bring it to the person who needs to talk. Okay, so without further ado, I think Lawrence is going first.
Yeah.
Okay. Yeah.
Okay, thanks. Okay, so you use microphone?
Yeah, if you'd like. If you
Okay.
don't want, you can turn it off as well. It's fine. Either way, it's good.
Okay, that's good. Okay, good. Hi, I'm Lawrence. Good to see you guys again. So today,
So don't forget, there's a scribe document, so everyone can scribe too. Okay, you can go to the week 9 prep channel. Somebody can fish it out and then put it on the general channel as well.
yeah, hi. So I was going through all the weekend papers on transfer learning, and I found that there's quite a lot of controversy. Then I also realized that we don't really have a good, I don't have a fundamental background. So I thought maybe I should do something basic, like basically talking about the transfer learning itself. What is it exactly? Because there's a lot of conflicting data I found. So, and again, this is not ground truth, but this is what I can get from the internet and whatever document I find. So what is transfer learning? So transfer learning is a technique that involves training a model of one task and then transferring the knowledge to a different but related task. Because in NLP itself, we're talking specifically for LLM, it involves training a language model on a large corpus of data, and then using the learned representation to solve the problems. Examples such as sentiment analysis and name entity recognition. I try to use a lot of examples so it's easier to understand. So then the other aspect is also fine-tuning. So there's a relationship between transfer learning and fine-tuning. So fine-tuning is a specific technique within the broader realm of transfer learning itself. So what is it? It takes a pre-trained model that's been trained on a large data set, and then adapting it for a specific task by continuing additional training on it on a smaller task-specific data set. So we refer this process to taking a pre-trained model and adjusting or tuning it for a specific task. Okay, for the primary objective was to improve performance and by leveraging the knowledge within the pre-trained model itself. Okay, so I give an analogy. What is transfer learning in real life? Example: if you learn to ride a bicycle, and it takes a while to learn, you fall, you get up, you figure it out. So later on in life, you decide to move on to the motorcycle. That's a little easier because the same balancing and the same issues you have when riding a bicycle, you already overcome it. So all you need now is know how to turn up the motorbike and additional controls. But for somebody who's never ridden a bicycle, going to a motorcycle will take probably a little longer. So the analogy of transfer learning is both the framework is very similar. I mean, 2 wheels, okay, and balancing. Right, so this is the analogy itself. So here's 2 diagrams. One is about fine-tuning, one is on the, let's see, this will be the right side, and the left side is on transfer learning. So you see the source model. So we take some features and we do some prediction on it. And to fine-tune it, we can actually take downstream and produce another new model. Whereas the pre-trained, whereas the transfer learning, we use a pre-trained model, but we only copy out the features and then move it to the same model. So the new model actually is not just being trained, but it's just only using the features only. And there's a difference between the fine-tuning and the transfer learning. So I will try to make sure we're clear on this one. So I break it out into like the definition, objectives, model architecture, the training process, the requirements, and then the computational complexity. So on the left side, you will see fine-tuning. What is it? Is it adjusting the previous model as discussed just now of a specific task? For example, we want to adjust the last layer of pre-trained model of BERT, for example, for sentiment analysis. And whereas in transfer learning, we're just using the pre-trained knowledge and move it just to a new model itself. For example, using pre-trained ImageNet model for a new animal classification class. Let's say you had a model to train on cats, and then you basically move it to, say, lions. So easier because cats and lions are very similar, right? So it's easier to use the same base model. Objective is, of course, fine-tuning is to pre-train it to get a bit more specific, right? So adapting a pre-trained model, example, pre-trained face recognition to detect specific emotions. Okay, because most systems have looked at face, but it may not look at various emotions itself. Whereas in transfer learning, we are just want to utilize some generalized knowledge. So applying, example, a model trained in English to understand legal text, for example. Okay. The other one is let's see, modifying some layers, often unfreezing the layers for specific specialization. Right, so you could do in GPT-2, you modify the last 2 layers of itself for a specific writing task, for example. Whereas in transfer learning, you're just using the existing architecture. You may free some layers yourself. For example, using pre-trained CNN for medical imaging, but without any changes. You're not changing the base model itself. For training process, for example, in fine-tuning, you're involving adjusting a specific layer of parameters. So example, you use VGG image recognition, VG16 for custom object task. Okay. Again, we'll talk about like cats and dogs, and now you maybe have something specific like breeds of dog or breeds of cat, and you want to use fine-tuning for that process. Whereas in transfer learning, you just only training a new layer. You keep that layer fixed. So, example, training only the layer for a new speech recognition task. The speech pretty much the same framework. Again, this is subjective to the type of language. Okay, Latin, European languages are easier and specific to them. Different from say CJK, Chinese, Japanese, Korean. The other data requirement is fine-tune requires specific data, task-specific data for the fine-tuning. Okay, example, needing a specific medical record to fine-tune a medical text classification. For example, looking at say breast cancer in the X-ray itself. Okay, how to identify versus maybe X-rays of lung cancer. Then in transfer learning, again, less specific task. Again, just use a pre-trained classification, pre-trained text, like that. Pre-trained text for general text classification. And lastly, we look at computation complexity. It's potentially higher depending on the extent of fine-tuning. You could tune for a variety of epochs and also amount of data set. So extensive training for pre-train is very specific, right, to scientific. Depends on the requirement. For example, very specialized scientific simulations. Whereas in transfer learning, you only need a simple quick adaptation for pre-trained method. Example, weather prediction. Okay, in one country and in another country is pretty much the same. Because that's basic differences. Oops. So when do we need to use fine-tuning? So fine-tuning, again, we'll break it up to whether you have sufficient data for the target task. Okay, so you have sufficient amount of label data for your task. You afford to fine-tune the task without much probability. And then whether the source and target domains are very similar or dissimilar. Because I'm going to break a little bit from the text here, so it's going to go through it. It's that in transfer learning, you are not using very specific data. You want to have a very similar domain yourself. So that way you are using the features from one to the other. Whereas in fine-tuning, you have to go a little bit deeper, right? You need to know more, not just the data. You want to make sure that for example, the model itself adapts with more detailed information. Okay, so things like unperformance is the transfer or the model adaptability. When you fine-tune with regularization, example, you can get overfitting if your transfer data itself doesn't have sufficient detail. There's insufficient target data. Okay. So the other thing is we have to talk about whether the transfer data itself, whether domains are very similar. So we talk about analogical inferences. So this is where we talk about the cognitive process of the transferring knowledge between the similarity, okay, of the object, the concept itself. So recognizing pattern of similarity and using this pattern to make this prediction, solving problems. It plays a fundamental role in the concept of practice transfer learning. So in other words, to decide whether the transfer learning is going to work, it depends how much difference between the target and the source material you're going to try. So example, just the diagram is like if you have a source versus a person and a source target could be a plant, a tree. So the question is, well, if the tree had an ear, what would it be? That one is, it's a bit of a joke, but you can't really connect the two. If you have to do this way in fine-tuning, it's no different because specifically you would fine-tune with all the plants and trees, and then they understand the tree is different from a person. Again, this is a very large table on terms of types of transfer learning. I put some definition on the left-hand side: inductive, transductive, unsupervised, multitask, self-taught. Self-taught would be like self-supervised. There's model adaptation. There is feature representation training, and lastly, we are fine-tuning, and as well finally pre-trained model itself. Because every model which is pre-trained, it itself can be very specialized to different tasks. So I've given a list of definition and examples. So rather than return to everything detail, leave these notes just to give you an idea. Okay, so the process of transfer learning involves the three main processes. You take a pre-trained model. Okay, you start one with trained on a large data set or related to a specific domain. Okay, and some example, BERT or Llama 2, which really understands in English. So that's easier to work with some language models. Okay, but some other model are multilingual. So not like GPT-3s, etc. Target tasks depends what the tasks you are looking at. So identify the tasks you want to perform. You have to be related to the source task in some way. So, example, classifying contract documents in the procurement, or when matter classifying the resume for different teams. Because the task itself, it uses a base data model. And then lastly, the domain adaptation. So the P-train model is used as a starting point for the target task. Depending on the problem, some layers might be frozen. The parameters are not updated. You don't need to do that. So what the advantage? Why do we need to do transfer learning? One, efficiency. Okay, it reduces the need for extensive data. So we don't need to regularly run the training system. It reduces our GPU power, right? So second is speed. You don't waste a lot of time on that. You just have to do some testing and error checking. See what the error rate is like. And then you can see whether the model is reasonably good in performance. Okay. And lastly is the performance. Because the task is already limited data, label data itself. So the advantages is basically time and money. Okay, and then disadvantage, of course, depends. It depends on transfer learning, not for everything. It depends very much on, for example, the domain itself. There's a domain mismatch, and if they're very different, and just on the analogy between the person and the tree, then will be very difficult. The performance will drop quite a bit. And again, it can overfit on a small data set. So that happens. Lack of interpretability, which means a deep model may suffer the lack of, well, I would say, transparency. You do not know why it made the decision that it made. Okay, it's hard to trace back. You have to look at the reason on the original model itself that you use as a base. And the other one is dependency on the source task itself. Quality depends again on the pre-train itself. If the pre-train model has biases issue, it can propagate to the target task itself. So lastly, transfer learning. We focus on transfer learning knowledge from one domain to another. And fine-tuning goes a step further by specializing the model to particular task. And we can consider fine-tuning to be a subset of transfer learning. We help to refine the final model of better prediction. So usually a lot of users basically take transfer learning as the first step, and then try refining it with fine-tuning further down the line to get a better result. Okay, thank you. Any questions? No?
So, but like just now when you talk about the disadvantages, right? They say domain mismatch.
Okay, so like for the part we asked about like domain mismatch, right? Where they say if you are not if the top and target domains are not related, then it will cause transfer learning to be detrimental to performance, right? This kind of sounds similar to like catastrophic forgetting in large language models as well. Where if you learn too many, I think if you learn a small set or subset or like no very small set of the skills, right, it might cause the model to actually forget some of the older skills. If I remember correctly.
Well, my opinion is not exactly that. Forgetting, you're saying like you train something and then you forgot what it was, is it?
Yeah.
Okay. I don't know if that's related in any way. Maybe, but usually for domain mismatch is when because the domains are very different. It doesn't even have to remember. It actually doesn't understand. I mean, again, the analogy between the person and the tree is if you only train on a person or animals or dogs, and then you try to use that same model for a different data set, for example, diseases in vegetables or types of flowers, that's going to be very different. Because if you can't understand it, you didn't have to forget because you didn't remember in the first place. I mean, that's what I think. Any other questions? So it's very basic, but getting started. No? If not next, who's the next speaker?
Thanks, Lawrence, again.
Yeah. Okay, thank you.
Hello, I'm Yanxia. Today I'm going to talk about the transfer learning, kind of overlap with some concepts introduced by Lawrence before, but I will in a perspective of large language models or language models. The material comes from this tutorial in NUS.WING 2019. It's transfer learning in NLP. I try to convert it to some concepts related to our class, large language models. So you can find all the whole tutorial here in this links. So in long ago, the transfer learning is proposed by, I think the concept is proposed by Professor Yanxia, who is a big name in data mining and machine learning. And he and his students proposed this, I think it's really a good survey. I read this before. They are formulating transfer learning as illustrated in these figures. In traditional machine learnings, for each task, we train a model. But in transfer learning, we are borrowing some knowledge trained from the source task and utilize them to the target task. This is the main concept of transfer learning. In the very beginning, a lot of researchers ask, okay, what's the difference between domain adaptation and with other multitask learning? So people, I think this is the Professor Yanxia and his students, it's Ruder. He came up with this such figure that to differentiate this concept. First, the two very popular concepts is transductive transfer learning and inductive transfer learning. These two words, transductive and inductive, comes from a reasoning format. I asked GPT-4 to provide me some examples. Yeah, they are very easy to understand, but sorry, I cannot, I didn't provide them here because we are limited in time. So basically, if we have same task but your labeled data is only in the source domain, we are using transductive transfer learning. According to the domains, are they in the different domains or the different languages? You can also separate them, classify them into domain adaptation or cross-lingual learning. Yeah, you can see the figure as follows. If we have different tasks, but we have labeled data in the target domain, we may use inductive transfer learning. And continue on. If our tasks are learned, we have multiple tasks, right? Different tasks. If these tasks are learned simultaneously, we have multitask learning. If they are learned sequentially, we have sequential transfer learning. And I guess in this tutorial, they will focus on the sequential transfer learning. But we are talking about in the pre-trained language model perspective. So, okay, transfer learning is that, sequential transfer learning is that we learn the knowledge, we learn from one task or one data set, we gain some knowledge, and then we try to transfer this knowledge into another task or data set. In the pre-trained language model way we are doing pre-training first to get some language models or this even this word to vector, the vectors, and then we do adaptation. I think this seems very familiar to us right now. So for the adaptation, I will recommend to check the week 2 adaptations lecture. Today I'm talking about following the tutorial. I'm going to take some example models from this pool, this language model pool, and to let's discuss how does they use the idea of transfer learning. In the tutorial, they are mentioning in the pre-training part, they are mentioning a lot of aspects. First, they introduce what is language model pre-training. We all learned about that. We have some objectives. We have a neural network, and we try to optimize our objective function and then get some parameters in the neural network updated and store some knowledge. But in the very beginning, we have word to vector. We have some vectors to represent each word. And then later, I think the representative word are word to vector and this word. So later we have some methods to represent a sentence or document. We can average the vectors of these words, or we can have a linear, we have a weighted vector to represent this. But we are today here, we are focusing on contextual word vectors, which means we want to consider the context information when we represent the current word in this context. This model called Kahoot is published in NeuroX 2019. It is very soon after word to vector and glove. The main idea is they want to pre-train a bidirectional encoder with empty task. On the left side, this sub-figure A, they are training encoder and with a decoder with cross attention, right? To do translation task. And later, they use this encoder for downstream task. This is the very beginning of the idea that we try to encode the knowledge learned from, we try to utilize the knowledge encoded when we train a relevant task. From their abstract, I found that their motivation comes from CV area. In CV, there has an image net that inspires a lot of work, and the CV has benefited from initializing multiple deep layers with weights, and it is pre-trained on the image net. But in NLP, at that time, we are using a vector obtained from word to vector to initialize our word representation. So this work propose this idea to utilize the knowledge we learned from training the neural network with machine translation task. And I guess this is how we can use this embedding, right? Previously, we already know we are using this encoder in the right side. This encoder is the machine translation pre-trained encoder. So how we use it is that we concatenate the glove embedding of the word and the code embedding, and just transfer this knowledge here in downstream tasks. Okay, this is the code idea, and to move on, we have another model called Elmo. This is very popular at that time because it shows us a lot of solid performance on a lot of tasks. At that time, our team is using for event extraction plus the word embedding. We are using glove and plus Elmo at that time. So the main idea is that you can see the figure here. We have a deep bidirectional language model. We are using encoder called LSTM, and then the main idea is we want to learn the linear combination of these hidden states to get Elmo representation. So we take these layers hidden states and do a linear combination and Elmo. This is one more step from COV. Okay, so we have a COV and we have a Elmo. What's the difference between them? I take the two figures of this model figures of this COV and the Elmo here. Anyone can figure out what is their difference. Yeah, please.
So a stick connection to the Elmo, right? Like the Elmo one, there's like the blue color one. You can skip the green color one straight to the lambda 2 blue in Elmo.
What, sorry?
Like there's some sort of skip connections, right? So like the orange, for suppose the orange is you can skip the blue and the green and then
Yeah.
the orange.
Yeah.
Yeah, then
This
the blue,
orange is just a here.
yeah, it skips. It's like sort of skip connection, like rest that skip connection where it skips.
Yeah.
You can do the same for the blue and the green. Is that the difference? But then for COV, you don't really see that.
I think you got the point. Yeah, this is the difference between COV and Elmo. In COV, we just use the last layers.
You press L for the laser pointer, then people can see where you're pointing.
Okay. So the difference is in COV model, we are taking the hidden states of the last layer. Which one?
No.
L, this one.
Okay, you go.
In Elmo, they are taking all the layers hidden states into consideration. Yeah, so this is the difference. One step forward. Okay, I will not repeat it because here. So this is the innovations over COV. Also, how we use Elmo different from COV. We don't just do concatenation in the final representation, but we concatenate the Elmo presentation in the very bottom layer of this target architecture. So we have a COV, we have an Elmo, and later we have a transformer, right? So in transformer area, a lot of models are proposed that we can embed a lot of knowledge into this model. Basically, we have, I think we mentioned that before in previous lectures, we have encoder-decoder models, we have encoder models, we have decoder models, right? So in GBT, I think GBT comes first. So in GBT, they are proposing that Okay, we can enhance or improve the language understanding by generative pre-training. So this is a generative decoder, but the language understanding part is achieved from this transformer architecture here. We have multi-layers of transformer block here. When we do pre-training, we have multiple objectives, text prediction or specific task related classifier. We'll not go to the details because we are looking at how does these models improve compared to previous models. So before we have a COV and Elmo, try to embed this knowledge pre-trained on other tasks to downstream tasks. In GBT, they are also doing this. The difference, I think the difference is also the transformer architecture used here. But I want to mention the differences between all the transformer related models. So in GBT, they are using one direction because they are auto-regressively predict the next word. So they are very good at the text generation tasks. But one issue here is one direction enough? So other researchers came up with a model considering two directions. Okay, when you represent one word, you consider the information on the left and the information on the right side. Anyone know what is the model who used the two direction information to represent a word? It is a very popular one. Two directional. Yeah, right. Yeah, that is
Bi-directional.
So this comparison figure comes from BAT paper. So I just take it here. So in BERT model, they mentioned that, okay, we think bi-directional encoding is very important. And so they done this BERT model here. I think this figure also sounds very familiar to you, so we will not go into details. I guess you know that we use masked language model as one training objective and the next sentence prediction. So compared with COV and Elmo, we are both learning sentence and word contextual word representations. The sentence representation. Anyone know where is the sentence word? No, I mean the sentence representation. Where is it? In BERT model, normally how do we represent a sentence representation? Yeah. The CLS token here, this is special token inserted in the very beginning, usually is taken as the sentence representation. Okay, so let's move on that. Just like Elmo, BERT can just be used for feature extraction. We have some input sequence here. We input them into the BERT model, and we get a lot of embeddings. But so we can have a lot of 20 layers. We have 20 layers encoders here. The one problem here is how we use this to represent a word like help, this first token. We take the final layers hidden states, or we take the middle the middle layers, hidden states, or we use all of them to get it. I think they also do some experiments on different ways to represent the tokens, So I think I can skip these details. I just want to know that they did some experiments to for this. After, so in transformer-based language models, we have GPT, this decoder-related model, and then later we have introduced the BERT. It is an encoder-decoder language model. Also here, BERT is an encoder, basically an encoder model. So we also have an encoder-decoder model like BART or T5. Here we just present T5 as an example here. The difference between T5 is from the other models in their structure that they are using both encoder, also a decoder. BERT is the encoder, right? GPT is the decoder, so they use both. I would like to skip these details too, so we can have a short class today. So there are also a lot of large language models starting from 2019. A lot are coming out. Here is there's a survey about large language models in the, I think in the early of this year. Yeah. I already mentioned in the very beginning that in the idea of transfer learning in NLP that we are using pre-training to encode these knowledges and then use adaptation to apply this knowledge into specific tasks. I will refer you to the week 2's lecture for this part. But for a quick question that anyone still remember what are the two types of adaptation, I mean fine-tuning here? What is the left figure represent? What does the right figure represent in fine-tuning? Please, or
The right one is it like Laura on the right side, or is it form tuning? Because it's form parameters, right?
you mean the right one is
Yeah, the right
Laura?
one.
Yeah.
Form tuning.
Is that Laura?
I don't think it's low ranking. That's the thing.
It is not a specific model. It is a type of fine-tuning ways.
Yeah.
It is parameter efficient fine-tuning.
It's like a more general.
Yes,
Yeah.
and on the left side we have fine-tuning because we are changing the parameters of the model here. Okay, the takeaway, I think it can be summarized in this slide, is that in transfer learning in NLP or in the language model area, is that we learn a model on one task and then transfer the knowledge into another task. We are using pre-training and adaptation to do this. I think all these are mentioned before in previous lectures. So that is all for my side.
Question?
Yeah.
I've got a question about so what does the pattern in the slides represent?
Oh, okay, that's good. Okay. So what is the question about call?
Because I understand for part A is the part where you are pre-training the bidirectional encoder with the machine translation supervision, right? But how about the part B?
Sorry, can you slow down a bit?
Sorry.
I cannot follow. Sorry.
Go and find the top left.
Well, this part we don't.
So like the part A part they're talking about, I think is related to the pre-training bidirectional encoder, right?
Yeah.
So how about part B? How does part A link to part B?
Oh, the encoder here is the encoder here
Yeah.
after pre-training.
Oh, so then
So the
how about
knowledge
this encoder? This is it from
Same.
Oh, so these are two of the
Yeah.
and both of them are pre-trained on machine translation.
Yeah, they are pre-trained on machine translation, but why I don't know. Yeah, I don't know why they choose machine translation.
That specific model itself has an encoder, or is it? So I think because I thought this encoder would be for the tasks, for the different tasks, you're merging all of them.
This part doesn't change. So
Oh.
how we compare them is that we in other tasks we are put the inputs into Glove. I get the word embedding and then go through the MT LSTM, the MT encoder.
Okay.
So we can cater to the very beginning Glove vector. So we get a representation of the word.
Oh, okay, I see.
Yeah,
All right,
this is
thank
the
you.
process. Thank you. Okay, thank you. Let's invite Victor for the study. Sorry.
Okay, I think I will cover the transfer learning for a specific task called dialogue state checking. So there's a very specific application of the transfer learning in one of the subdomain of the research. Okay, so after the previous introduction of transfer learning, I just make some conclusion. Okay, so there are several of the summary of transfer learning. For example, the first one summarize transfer learning as summarization transfer learning and domain adaptation refers to the situation where has been learned in one setting and exploit and improve the generalization in another setting. We have another summary called transfer learning is the improvement of learning in new tasks through the transfer of knowledge of a related task that already been learned. And another summary is that in transfer learning, we first learn base network on a base data set and task. Then we propose the learned features or transfer them to second target network and to be trained on a large target data set of tasks. This process will tend to work if the features are general and suitable to both base and target tasks instead of specific to the base task. So you can see that actually transfer learning is to learn from one and try to apply it to another one. But in order to apply it well, the two tasks or two data domain need to share some similarities. Okay, so and now I'm trying to introduce what is the task of dialogue state tracking before we talk about the application. Okay, so here I show an example of dialogue state tracking. So it's a very critical task in natural language understanding. And you can see that in the dialogue history, the user and the system will take turns to interact with each other. And what the dialogue state tracker do is to trying to locate the information after each turn of interaction. Okay, so for example, the first turn they talk about they want to find a cheap restaurant in the center of the city. So we trying to log down those key information. That is for the restaurant domain. For example, the price need to be cheap and the area need to be centered. So such a process is called dialogue state tracking. So we actively track what is the dialogue happening. Okay, so is generally applied in several of the daily scenarios like restaurant reservation or ticket booking. Okay, so as we see that the goal is to extract goals or intentions expressed in conversation. And recent years, there's a very popular topic called zero-shot dialogue state tracking. That means we do the dialogue state tracking without any label data. we don't have training data, we directly do this task. And it's a very challenging, and we have seen a lot of methods of high transfer learning to solve this problem. Okay, so firstly, let's see. Let's trying to understand why transfer learning will work for this specific task, and intuitive explanation is that based on the slot already learned in one domain, a DST model is able to directly check those slots that are present in the new domain. For example, if a model is able to check the departure slot in the train domain, so when is the train departure, it should be automatically or should originally have the capability to transfer to another domain, like train domain there, which also have the similar slot type as the departure time. So it's as I said before, they share some similarities. And the second thing is that how we can use transfer learning to improve the performance of zero-shot DST. Okay, so from previous summary, we can see that usually we can do it in two ways. The first thing is that we transfer it based on model trained on similar tasks. And the second way is that we can transfer it based on model trained on similar data. So I will give example of both of the models who are in transfer learning for zero-shot DST. Okay, so firstly, let's understand the some of the baseline. The base model we talked about just now is T5. T5 is called text-to-text transfer transformer. So it's joint trained on 4 different tasks, which is machine translation, classification tasks, regression tasks, and the sequence-to-sequence generation, like document summarization or even the question answering. So you can see that T5 is already trained on several different tasks, and we are trying to make use of those different tasks for the transfer learning. Okay, so for example, can we easily train T5 to do the QA task? I think that will be very easy, right? And if we can transfer the DST task also in QA task, that means we can use the model T5 for the DST task, and we can do it in the zero-shot way. So the reason why we are using QA task as the task that we want to share between different area is because QA task is relatively easy and it matches the sequence-to-sequence format of the pre-trained language model. And also the QA problem has a rich data set, and we can use for the training. And the train model you can be directly applied to the DST task. For example, the QA is that we ask question. We ask, okay, some of the extractive question is we directly get answer from the model. You can also ask some multi-choice question if you have several options for the model. So if the model is trained already on the QA task, we can try to transfer it to the DST task. So how do we transfer DST task? For example, if you want to track the departure time of the train or taxi, you can directly transfer it to question. So we ask the model, what is the departure time of the taxi, or what is the departure time of the train? We can also ask what is the stars of the hotel, and we expect the model to give us some answers. So such a process, by transferring the capability of a similar task, we call it cross-task transfer. Okay, so here I have a question. Can you think about other tasks that can be used to transfer the knowledge so that we can apply the zero-shot DST? So I just said QA is one of the tasks. Is there anyone you can think of?
So Victor is asking about other tasks. Right?
Okay, yeah.
Because I think like this is really QA, right? The focus is to take knowledge intensive like tasks and then try and use that to give the model knowledge or give some sort of knowledge, right? So that you can use for dialogue state as well, right? So maybe like fact verification, like people.
Fact verification, right?
Yeah.
I think it is okay, but fact verification needs a lot of like detailed tasks to achieve, right? Can you think about anyone that is like as detailed as like QA, such kind of task? Because fact verification can be done by a lot of approach, right?
Yeah.
Yeah. Can you think of one of the approach that may also help this one? So I just say, yeah.
Is there a chat, or is that?
Okay, let me check. Okay. Mass language modeling. Okay,
Mass language modeling, it can work. Yeah. So But I was considered the most language modeling is some tasks before the test-to-test generation model come out. Yeah, so before that, we cannot directly ask the model for text output, so we just mask it and ask for the prediction. And yeah, is there any more answer? I think that's right. Yeah.
Any
Yeah.
melody recognition.
Oh yeah, yeah. That's also related. Yeah, and
Also relation, also like those relation data sets. Like I
Mm.
think the last week lecture on llama or something.
yeah. Okay, I got your point. Yeah, I think it's okay. It can work. So I just give you another several ideas. Okay. Okay. Okay, so actually you can see that a lot of tasks can be used to do the cross-touch transfer. So for example, prompt tuning. So you can try to tune a prompt, train on a similar task, and then you use the same prompt for the DST task. And you can also do the summarization. So for example, they already asked the model, help me summarize the dialog states, or help me make a summarization in the standard format that I can use for dialog state tracking. Or you can use the instruction tuning also can. So you can just give the model some instruction, and you can also include an example of the DST work, and you can use that to get the model through the DST task. So most of this has been proved to work well on the zero-shot DST domain. Okay, so besides we are using similar tasks, I will also mention another thing that we can also do transfer learning using similar data. So this is strongly related to the data structure of the data set itself. So for example, in the multi-words data set, which is commonly used for dialog state tracking, we have 5 different domains, and which are attraction, hotel, restaurant, taxi, and train. So among them, we can see that some domains, they share a lot of similarities. For example, the taxi and train, right? They share a lot of common stuff like departure time, departure location, arrival time, or arrival location, or the destination, right? So those similarities or those similar slot types can be used for us to transfer the knowledge from one domain or from the source domain to the target domain. So this is also a very common way to do that. So how do we do that? So we can use this called leave one out setting. So we leave one domain out, we use that one for testing, and we train on the rest 4 domains. And yeah, those domains that we train on is called source domain, and we test on the target domain. And such a process is called cross-domain transfer. Yeah, so these are 2 very typical way we use transfer learning in the specific DST task. And also for the result, right? I want to show you all the results. Just show you one of the chart that we do the comparison between the seen domain and seen domain. So the seen domain means those domain has already been seen in the source domain, and unseen domain means those domain that only exist in the target domain. So those unseen domains should be relatively hard for model to predict. But if your model is let's say pre-trained on a QA data set, and QA data set has already quite well described what are unseen slots, so you can also be comparable to those seen domains. Okay, so just as I mentioned, because we try to use similarity between different domains to for the cross-domain transfer learning, and we should also compare them differently to see if your model only benefit from the seen domain or can also benefit from unseen domain. Okay, so that would be most of my presentation. So as a conclusion, I just introduced you actually we can apply transfer learning to the specific task called zero-shot DST. You can apply it in 2 different ways. One is called cross-task transfer, and another one is called cross-domain transfer. Transfer learning is very suitable for the zero-shot task because especially for the DS task, because these tasks share common or similar slot types across domains, and it's also suitable for the text-to-text generation format. And transfer learning can be used for many zero-shot research because it can save the cost in the data and can also save the cost in the training. And yeah, that'll be all for my presentation. Thank you. I think any question? No.
Questions from anyone?
Okay, so I think we have one more presenter who's not available, right? We may just play his video.
I think make it bigger.
This one.
Hi, so my name is Wei Soon.
and today I'll be talking more about meta transfer learning. Just a disclaimer, I'm fairly new to this topic, so I may or may not have gotten some things right. So if there's anything that anyone wants to clarify or correct me on, please feel free to do that like through the comments or Slack. So wait, what? Yeah. So you may be wondering what transfer learning is. Of course, I'm sure many of you already know what transfer learning is. So I'll go through the meta portion of meta transfer learning. Yeah. So firstly, we kind of learned a little bit about meta learning in week 3 as termed in context learning.
It was because it was on laser pointer mode, so I
so the idea of meta learning is that if you have already learned 100 tasks, can you figure out how to learn more efficiently? So the idea is to learn how to learn. Yeah. Meta learning can be applied in many different ways. We can learn the optimizer, we can learn the RNN that ingests the experience, we can learn like word embeddings, representations, how these are formed basically. So then this can be applied into many different types of machine learning, not just language models like reinforcement learning, image detection, stuff like that. Yeah. So conventionally, we find algorithms that work best with our data, and then we train them off historical data to later predict our outputs, right? So according to Venstrom, meta learning aims to obtain these things called meta learners that adapt a lot more quickly to different tasks and a lot more diverse tasks with very little data. So in other words, like few-shot learning. Yeah. So the challenge in meta learning actually is to learn from a prior experience in a systematic data-driven way. So you first have to collect metadata that describes like prior tasks and prior models. So these comprise like maybe say the exact algorithms, the hyperparameters, the pipelines, maybe even like the architecture. And these are known as meta features basically. So these can be put into new optimal models that can basically tell us more about or predict better on new tasks. Yeah, so specifically in NLP, in LMs, this can be applied to a whole bunch of different language tasks like relation classification, natural language generation, and so on. Yeah. So there are many benefits of meta learning. The idea is that learning how to learn any task is a lot better than knowing how to learn just one specific task. So meta learning, the idea is to acquire a lot more correct features from smaller data sets. So these are extremely effective in few-shot learning and generalizes a lot better on a new diverse set of tasks. So in this sense, it's quite similar to multitask learning. And for LLMs, it like GPT-3, stuff like that, it implicitly uses meta learning. So this is termed in context learning, like we've learned before in week 3. Like you can refer to those slides for their details. So let's go more into about how it works right now. So meta learning effectively trains on a set of training data rather than individual inputs like in traditional supervised training. So I couldn't really find a diagram that represents meta learning in terms of language models specifically. So I thought to explain it using images first, so it's more digestible, the concept. Yeah, so in conventional supervised learning, you have a training set, you have a test set. In meta learning, however, you have a set of training sets and you have a set of test sets. So you end up learning how the model predicts the training data to predict the test set, rather than simply learning how to predict a single label, like a single classification. So in this sense, you can think of it like as meta learning occurring one level above conventional machine learning. So the model can train on these sets of training data, learn how to predict the the test set output, then eventually you'll be able to predict well even on a set of data that you've never really seen before. Yeah, so the difference between supervised learning, like regular supervised learning, and meta learning can be effectively summarized by these two statements here. So, as mentioned before, meta learning takes in the training set, D-train, in addition to the regular image X, like in supervised learning. Then it produces our output, which is the label for our test set. So then maybe you start to wonder how these training sets can be incorporated, right? So you can create this training data in many ways to feed into the model. The easiest way to visualize this is through RNNs. So if you take like generic learning as a function of the training set, after minimizing our loss, you get data star. So in the context of LLMs, you have maybe say a training set D-train on some kind of corpora, then data star will be the function we get after training the model, which is to be used for some arbitrary task. So if you take a look at the RNN here, meta learning, you can kind of visualize it as such. So with each node containing what is a function of the previously learned data, so the data star. So these separate functions act as the parameters to the meta learn model, which eventually feeds into the inner layer for some task I. Then you combine this with the output X, the input X, which gives us our output Y. So there are many other kinds of meta learning techniques with different notions of eventual output function. But for simplicity's sake, this is the easier to understand. So let's move on to meta transfer learning. So according to this paper by Xuan, meta transfer learning aims to combine both the benefits of meta learning and transfer learning. It helps deep neural networks converge faster while reducing the probability of overfitting on future training data. So in a nutshell, you can think of it as meta learning, how to effectively transfer. So the way you do this is through a set of operations called scaling and shifting on the large scale deep neural network weights. And in this particular context, which can be applied for a range of different things, in this particular context, it's for images. But this idea can be applied to many different realms in machine learning. But effectively, transfer learning refers to adapting these deep neural network weights through the set of operations, which is scaling and shifting, while meta learning refers to the learning of these hyperparameters used in the scaling and shifting operations. So the performance boost of this method is quite obvious. With the model agnostic meta learning, NAMO, one of the most popular models in meta learning, having converged only after 140K tasks compared to 8K using meta transfer learning. So as you can see from the graphs, these converge very quickly using only about like 8K iterations because each iteration consists of 2 tasks. That's what they said in the paper. One of the most popular models is NAMO. We converge only after 240K tasks, which is like totally out of the graph. But this meta transfer learning also consistently outperforms many other models, which proves the theoretical worth of such a strategy, as you can see here in this second diagram. So learning how to transfer compared to simply learning through transferring. I won't go too in-depth into how meta learning is achieved in this paper, since it's quite intricate and time-consuming, but you can read the paper if you like, because there are quite a few interesting methods described that further optimize things like how they actually perform the scaling and shifting mentioned previously, which actually drastically reduces the number of parameters necessary compared to normal meta learning. And this strategy called hard task meta batch, which is kind of how they pick out the hardest tasks out of the batch of predictions, then feed it back to further strengthen the model. Okay, so moving on to the crux of our course, LLMs. Pre-trained language models, or LLMs, they offer significant improvements in performance on various text classification tasks. So in this paper by Wang et al., they talk about this thing that they proposed called meta-distance transfer learning. So the problem was that PLMs, pre-trained language models, they have extremely good memorizing ability. So these may memorize non-transferable knowledge, even for the target domain, and then suffer from negative transfer. So when there exists like large domain gaps and very different class labels, transfer learning is more likely than not to fail, to not succeed. Yeah, so the question remains, how can we transfer knowledge across different domains with different classification targets for a pre-trained language model-based text classification? So here is a motivated example to kind of visualize what this meta-distance transfer learning is. So we have two sets of data, right? We have Amazon product reviews, and we have this data set called SST5, which is about like movie reviews. So traditionally, we would fine-tune these two separate models to achieve a model that predicts for each particular task. However, with meta-distance transfer learning, even though these two realms are, let's say, quite different, you have Amazon product reviews, you have like tiny intricacies that are like, it's for products and not for movies, So even though the sentiment can be quite similar, the outcome is really different. So the idea is to meta learn using one single model and then fine-tune it respectively for each task. So the way that they did it, they proposed 3 steps in the paper. So the first step is a task representation learning. This employs the idea of prototypes. So prototypes effectively is a method to characterize class information with concrete representations. So related points tend to cluster towards one prototype, one single representation when mapped to the same embedding space. So visually, we will end up with a space like in this diagram, where we have multiple prototypes related to specific task labels. So this function on the right here, it kind of just shows us how we get the typical vector Pij. In layman's terms, it's kind of just a average of this function, which is a embedding function that encodes both the texture input and its class label. So texture input, class label. So in the diagram, you can kind of think of it like you see here, there's this average of the different embedding functions. So in the diagram, this embedding function can be represented by this pre-trained task encoder here, which gives us the different prototypes. Yeah, so on to part 2. After they successfully map this onto a space, we get the multi-task meta learning training. So we represent prototype vectors in a meta knowledge graph, meta KG, as described here. So what we will do is we will query this training assets to get a meta knowledge. So meta knowledge is effectively a scalar value that tells us how transferable the training instance is. So the higher this meta knowledge value, the more desirable it is for the meta learner, since these instances can generalize across like a wider set of tasks. Then to prevent overfitting to specific tasks, we create the meta controller, the same, to balance out the innate bias towards these training instances with higher meta knowledge values. After that, we put them all together to get our meta learning. So then finally, we have the task-specific model tuning. So in this step, we just take the meta learner that we obtained in the previous step, we fine-tune it to generate multiple different classifiers for the different tasks that we had in the beginning. So if you recall the example, the motivator example that we had, we can fine-tune to create models specific for our Amazon product reviews and our SST5 movie reviews respectively. So effectively, this model
is generalizable across many different domains. So that brings me to the end of my section on data transfer learning. Thank you.
Okay, so do we have any discussion or questions that we'd like to talk about for meta learning? I think Victor has been supervising one meta learning project under our group. Do you want to say anything about how work is going in that project?
You want a microphone? You want a mic?
Okay, maybe I'll say.
Yeah, that's it.
Yeah, so I think meta learning is a very interesting technique. It's some of what we're talking about in transferring in general. So I think it's useful to understand the concepts and then think about like where the border between meta learning and what type of data sets work well. I think all of these techniques, when you talk about distance supervision, transfer learning, and meta learning in general, they're all versions of each other, right? So you just need to figure out like which border applies for which types of tasks, right? So when you think about machine translation, are these tasks that are adjacent enough that you think these are transfer learning tasks or these meta learning tasks? Or if you think about like what Victor was talking about before about DST having associated tasks, right? Are these close enough that you would think that a certain type of meta learning or distance supervision or transfer learning would work better? I think, you know, when we see all of these materials, we understand the concepts, but we also have to think about like, if I were to step away and I need to go into industry or I have a project to do or something like that, which technique would work? So I also want you to think about the parameterization in terms of like, say, data, right? Because a lot of this is predicated on data, right? You need enough data and the data has to be of a certain quality for that to work, right? Because if you have a lot of data, but it's noisy, probably you're going to spend a lot of cycles not getting anywhere, right? So anyone would like to offer any words or advice? Yeah.
Thank you. Just want to introduce myself. I'm actually from industry, from the healthcare. So I do a lot of facing a lot of tasks. Actually, the vocabulary itself is never learned by most of that language model. So that is become like the biggest task actually is to how to do the effective transfer learning. And limit of all the, as Professor said, clean data. Usually nobody really pay attention to accumulate those data. The same way, there's also domain-specific data for sure on the internet, like the PubMed, which use all the published paper for that purpose, but actually that's only fit for certain purpose only. So actually for my personal learning, I really want to see that how actually what is the effective and efficient approach to solve some tasks. Sometimes it can be very simple. Let's see how do you you know, get a model actually to predict the words, which is a very special and very confusing word to any people outside the industry. Yeah, so it's just a comment here. To me, this is probably the most important topic for the whole module.
Can I get your name again? Yeah. Jonathan. So let's just take this up for a couple minutes because like today we're lucky in the sense that we didn't take up too much time. What do you think we could do if we're faced with this problem where we have vocabulary that is in a silo, right? It's not out there on the web, it's not well indexed like healthcare information, right? Then where do you think we can apply? It doesn't have to be transfer learning, but like where will we get that data from in order to leverage the power of a language model? So do you think we should, yeah. Yeah, so it could be any type of research, so resource. So Yanxia was asking like, I'm not really sure where I could get the vocabulary from, right? So are we talking about online data or from another source? Is that what you're asking about?
Some internal documents.
Some internal documents, Jonathan is saying that maybe there are internal documents at the provider source or the client source that might have new vocabulary that we've not seen before. Yeah, go ahead, Mark.
So I thought there would be some sort of lexicon or dictionaries specific to a particular field. Like if you talk about medical, there are very many fields and they are very complex terminology. Some of them are fairly new, but they are, and so these, if you can digest these as the data itself for the systems to get reference back, that could help. Otherwise, it will not understand a very specific term or how the terms are used.
Warren, you wanted to say something in addition?
Yeah, I was thinking like something similar, but just like simple, if you have a way to like, let's say if you are given a definition of the word and how to use it in an example, right? We could probably generate some synthetic data using like another language model.
Synthetic data.
Yeah, but then you need a lot of quality control because
Yeah.
yeah. So if you have that, if you are able to get the quality control, right, you might be able to generate like a larger like data set, which you can then extend to your original like scarce data set. And people are doing that as like science in different like fields. I think like platypus, there's a people call platypus where I think they use synthetic GPT-4 data and then use it for like sex and QA answering.
Okay, so Warren brings up another point about, generating or hallucinating data,
Yeah.
right? So that might be a good source. Why? So I'd like you guys to reason through this. Like we have proprietary data. We don't want to reveal to outside source, right? So you could say, oh, I'm going to generate a model on this proprietary data. It's going to be very weak, okay, but it will have statistical information about the corpus, but I won't be able to de-identify any document of it, right? So I can use this as a generative model, for example, to hallucinate new data, because actually what I want is, I want the statistical properties of that data to exist in the model that I want to treat in production, right? But I don't want to reveal the data that I have I don't want to review my cards, so to speak, right? I hold my cards close to my chest because they're my IP. Right, but I don't mind giving statistical data. Oh, this deck has like 42 cards, not 52 cards. Okay, so it's a little different, right? Okay, so that's one part. Other reactions or points that you guys want to make? So I still want to try to connect this back to what we're talking about today about meta learning, transfer learning, what things that we can think about. So I think Jonathan's point is like when we are faced with out of distribution work, right? And all this discussion is like, we have a task that's already trained, right? We want to bring that task and say, just like I have to retrain an office worker for a new task, right? We want to take what they already know and say, okay, here's an analogy, right? A lot of transfer learning is about analogizing things, right? Then what can I do?
There are some words where they can actually utilize the embedding or the representation from the large language model. Like if there is a new domain, but the symbols in that domain can be represented by the text or tokens, then we can utilize the representation learned from the language model to represent those symbols. But we need to use the rules in that new domain to learn the relationship.
Okay, so it needs to have the same representation shared. Otherwise, we have something lost, right? So transfer learning addresses that well because you already have a model that's already trained and you're trying to transfer in information coming from a new domain. All right, let's go ahead.
I was looking at how medical data, for example, we use because of the other lexicon itself. So one way, it's just what she said about the embedding itself. There's now getting popular to use vector databases for that particular purpose. When you take the embedding out and you basically put in to the vector database for do a very fast similarity search narrow down the specific meaning. Take for example, if you have a specific problem, a disease, what is associated we call treatment for it. The treatment itself may relate to, for example, side effects of the treatment and the cost of treatment itself. So all these are related within that vector itself. So that search is a lot faster than trying to use an LLM for that purpose. I think there's a medical company that's specific in the area that doing the tremendous amount of interest and funding, like literally like 3 months.
Yeah, so Lawrence is talking about vector space retrieval methods, like using KNN or something like that on top of that, right? So we can go the direct route by looking at the vector representation and trying to find things, right? Or we can go the indirect route and do it through an LLM, right? To say I have tasks like what Victor was presenting earlier with T5, right? And I want to transfer in other things to say, okay, I have a new distribution of data. What tasks that I've already performed can be amendable to use on this new data, right? But one thing I think we haven't touched on that's really crucial is that for out of vocabulary, there is one thing that we really need to think about, and we did cover it, but it's a while back. Does anyone remember what we need to make sure? Like Yushi mentioned embeddings, right? So embeddings, we need to make sure that they have the same underlying representation, right? Yisong, go ahead.
I thought you were going to say subwords, so at least.
Yes, I was going to say subwords, so you got it right. You know, okay, like tokenization, right? If you don't have the same type of tokenization, you're dead in the water. Okay, because all tokenization is necessary as a precursor step to building embeddings, right? If you don't use BPE or something that's common between your base model and your other data, you're sunk. Okay, and that's a very big problem if you think about it, because BPE is a data-driven algorithm, right? And if you're running BPE on general web stuff, it's going to look completely different from healthcare, right? Because you know, healthcare or any like sciences, you'll have all these Latin suffixes and prefixes, right? So the BPE algorithm is going to come up with completely different tokens, and the distributions and the statistics will be completely different. Right? So we have to worry about these very basic things and answer them well in order to do things like transfer learning upstream, right? Because if we don't solve these problems at the beginning, we're starting off on the wrong foot. You know, you're trying to run a sprint, but you're not wearing shoes, right? So it doesn't help. Okay, so I think when we think about distributions of data, you always want to come back to that and ask yourself, does the data look the same, right? Because if the data looks the same, then I can think about transfer learning. And I'd like you to also think about, okay, we are doing transfer learning for LLMs. Can I do transfer learning for tokenization? Okay, can I learn like a distribution of tokens, subwords, okay, transfer it into my model, right? Like I've seen some Latin stuff, but not so much like I have in medicine or other terminology, right? Because we have a lot of compounds. In fact, I would say some of our medical terminology looks more like noun compounds in German, you know, because they just all glued together, right? Rather than have spaces, right? So I'd like you to think about that as well.
So,
yeah,
using a base of chemical names. So in biochemical, basically it's the same except same base, and we're talking about tagging it together and how that relates back, right?
Yeah. So we can get another corpus like a chemical corpus or something comparable to distribution, but we still have this problem is that we cannot transfer embeddings because the embeddings are based on BPE or other tokenization.
Okay.
Right? So we still have to figure out how to take the tokenization that we have with our giant model, wherever it was trained on. Let's say it was T5 or something, right? It's trained on millions or billions of tokens. And I need to move it over so that I can effectively represent Jonathan's or Lawrence's corpus, right? Because without that, we're not talking the same duck language. You're speaking duck, I'm speaking chicken, right?
Both of us.
Go for birds, right? So we're still talking English or Latin stuff, so it's not like CJK languages,
Yeah.
right? So it's not so bad, still in the same Unicode Latin alphabet.
You're trying to kind of align both the embedding spaces together into the same embedding space or something like that.
Yeah, so I'd like you to think about that, right? Because we are talking about transfer learning, but we're assuming the same subword tokens, like Yisong said, oh, I thought you were going to say subtokens. I am, right? So we come back to that critical point that we have a shared understanding of what our vectors mean, right? Because if you run the vector space embedding again, but with different tokens, your dimensions don't mean the same thing. So it doesn't make any sense to say this vector is close to that vector at all, right? Yeah, Jonathan.
Yeah, very basic questions here. Because we're talking about language model that has huge space, we talk about embedding. That is actually a very topic words actually tiny embeddings here. So this actually is totally different scales here and
So Jonathan, I didn't quite catch you. You said that the embedding space is very large, but the number of tokens I'm embedding are small. I'm sorry.
for the pre-trained model, the embedded space is huge. It's a huge space here, and for the the special words or special domains, the embedding can be very small. Then it's actually we are actually basically talking about the ocean, something like that.
Right, okay, I get it. So because these words are very rare, they don't have a lot of context, so I don't have sufficient statistics to figure out exactly where they go in the embedding space. I mean, I will get an answer, but it's sort of fairly gross in the sense that it's quite uncertain what the statistics for these tokens are, right? Yeah, so I think again, the key part here is tokenization, right? You have long words that are from healthcare, and you can decompose them and say, instead of just using subwords at an English level, you can say, I want to find macroscopic subwords, right? So instead of saying, I look at just a sequence of subtokens, I can say I have hierarchical subtokens, right? So, like the letter A as a prefix usually means negation in Latin, right? But then I can say anterior or anthropo or something like that, and that helps me understand what that suffix is, even though it's a hierarchical, right? So maybe that would help us get more sufficient statistics, right? And it would also dovetail into what we have in standard English, because a lot of our standard English also shares some of those same parts, right? So I think this is a very interesting thing to think about. I mean, again, we have time today, so I just look it up. But I think for a lot of topics, because we ran out of time, because it's always past 6, right? We can also stop to think, okay, if I would apply this in a commercial context, or if I vary this, or if Prof was actually giving a final exam, right? Like, what would that question look like? Like, if I were to take Jonathan's question in healthcare and say, okay, you guys have all studied large language models. Tell me how you would build a large language model and transfer it from T5 or something. Okay, and I would ask you, okay, what strategy do you use? How do you solve that problem? Because that is the real question. I mean, who cares about the technical things in the paper? They're going to stay there. You're going to figure them out, or if you don't want to figure it out, you can ask ChatGPT to tell you, right? But you still have to come up with a strategy, right? The strategy of being able to utilize that knowledge at a meta level, right? So we're doing our meta transfer learning in class right now. Okay. All right, so let's thank all our presenters today. Okay, so thanks everyone. Make sure you get your sprint 3 out if you can do it. Okay, I know I'm not very strict about a lot of things in this class. Again, the whole point is to give you a lot of exposure and to help you network with people, because again, Singapore is a small place. After a while, you know everyone in the community, so it's good to bootstrap that by having a course like this to put my research group in touch with all of you, and likewise. Okay, so we'll see you next week for week 10, and yeah, until then, let's hope you can get your deliverables for the project, your name, your student number, your email, okay, and for your team name, your team abstract. Okay, those are the two things that I need. Okay, if anyone hasn't figured out their project yet for whatever reason, let me know. Okay, you can just DM me and I'll take note to talk with you. Okay? Thanks, everyone.
I thought my thank you. I thought you had a good inventor.